So let me start with the concept of vector space. So this is, a frightening word for most of the people, but I think it can be less frightening if you think of it as just a set. So a vector space is just a set containing certain elements that satisfy certain rules. So let's talk about it. So let's say we have some set. Suppose there are some elements like A, B, C, etc. Some V, W, and so on. So this is a vector space is just a set. So it's a set that has some elements in it, and these elements satisfy a certain criteria. We will see it shortly. And to be consistent with all the notations, the elements of this set will be represented by this special notation. It's called Dirac notation. So these V will be represented by this. This is called a ket. So all the elements of this vector space will be represented by this ket. So this set V is a vector space if it satisfies these things. Number one, that is closed under addition, which means that if you add any two elements of this set, for example A and B, and whatever the result is also contained in this set. Number one. And number two is that there is a null element in it. Let me represent it by N. Some people would represent it with the 0, but since I'm using 0 for my 0 state, which is not the null vector that I'm talking over here, so I will not use this symbol but use N. So this is just a null vector. And by the way, the elements of this vector space, they're called vectors. So there is a null vector N such that if you add it to any other vector, you get the same vector back. Okay, so this is a null vector. You add it to any vector, you get the same vector back. So this is the second condition that this set of vectors need to satisfy. And then there is this third option, that third rule, that it is closed under complex. It's closed under, let me just write multiplication and then I will by a scalar. It means that if you have some scalar, S, and you multiply it with some vector A, the result is also part of this set. Now, if this S is only real, that you can multiply it with 1, 2, 3, 2.5, etc., then this is called a real vector space. And if this S is can be a complex number, then this is called a complex vector space. In this course, we will be dealing with complex vector spaces, which mean that this S is a complex number. So by the way, if you combine this and this axiom, then it means that if you have something like alpha plus beta, so this alpha into some vector A, this is also part of this vector space. This beta into some vector B, this is also part of vector space. And if I add them according to the first axiom that it has to close under addition, it means that this sum is also part of this vector space V. Okay, so these three things have to be satisfied by this set. Let me take an example. So let's say I take an example of a complex vector space C cube. For example, I can have a set that contains elements like this. 0, 0, 0. This is a column vector. 0, 1, 0. 2 plus iota 3, 0. And so on. You can think of any column vector with complex entries with 3 elements, and that is part of this set V with all the real number. For example, even 2.1, -1, 0, this is also here, and so on. And we can see that this is a vector space because there is this null vector that I wrote just in the start. And then if I add any of these two vectors, then the result is also part of this. And if I multiply it with some complex number, the result is still part of this one. So this is one vector space. So we have this special name for this. This is vector space over complex numbers, and its dimension is 3. We'll see shortly what the word dimension means. You can also, think about another vector space, let's say W, which has elements like this: 0, 0, 1, 0, 0, 1, 1.1, 0, 1.1, 2.1, like iota, -2, and so on. This iota, by the way, is -1 square root. This is also vector space, and so on. And similarly, you can construct, a lot of different vector spaces. For example, if you can restrict them to be just real numbers, this is this W then is just this plane, right? Because in this real plane, all the vectors, they can be represented by these column vectors of 2 by 1 size, because this vector has an x component and a y component, which you can write like x over here, z over here, y component over here, and so on. So all the points of this real space can form a real vector space of 2 dimension. But we can also have a complex vector space of dimension 2 if we allow these elements to be complex numbers. Okay, so anybody who doesn't get the idea of a vector space? Good. So let me summarize it again. A vector space is just a set that contains elements, and those elements are called vectors. If it is closed under addition, there is a null vector, and if it is closed under scalar multiplication. If it contains complex number, it's called a complex vector space. If it contains only real number, it's a real vector space. Perfect. Let me now define a couple of terms that go on with the vector spaces that we'll be using. The first and important term is what we call a basis. So a basis is a set of vectors. Let's say v1, v2, v3, and so on, that you can use to write any other element of that vector space. For example, if there is some vector v, I can write it as some of these basis vectors. So some alpha 1 v1, some alpha 2 v2, some alpha 3 v3, and so on. And just to give you a concrete example, if we talk about the real plane, then I can have this unit vector. It doesn't have to be unit vector, but let's say unit vector, this I hat, and this unit vector j hat. So this I hat and j hat, they are my basis vector, because any other vector a can be written as some number 2, let's say I, plus 3j. So these 2 and 3, they are this alpha 1, alpha 2 that I have written, and this I unit vector, j unit vector, these are like v1, v2, etc. that I'm talking about. Okay, so in general, these v1, v2, v3, they do not have to be orthogonal, but usually we choose a basis such that these v1, v2, v3, they're orthogonal. Orthogonal geometrically, if you want to compare with this real plane, you see this I and j, they are perpendicular to each other. It means that if I take a dot product between I and j, I get a 0. We'll soon define an equivalent of this dot product for vector spaces. But for now, you can imagine the definition of orthogonality similar to this, perpendicularity. Perpendicular is a geometrical, a word that have geometrical significance, and orthogonality is a bit more general than that. Okay, so the number of elements in the basis, they are called the dimension. If there are like 4 basis vector that you need to represent any other vector of the vector space, the dimension is 4. If it is 3, the dimension is 3. And if I go back to this C3, or you can see that you can represent any vector in this vector space by using only 3 basis vector. And let me write them down, which one of those. So for C3, if I have V1 like this, 1, 0, 0, V2 as 0, 1, 0, and V3 as 0, 0, 1, I can represent any vector V. For example, if you have this vector V2 plus iota minus iota 3, you can represent it using V1, V2, V3 like this. 2 plus iota 1, 0, 0 minus iota 0, 1, 0 plus 3, 0, 0, 1. So this is, your alpha 1, this is V1, alpha 2, V2, alpha 3, V3. So you see the dimension of this is 3 because using these 3 unit vectors, I can represent any vector V in this space. And by the way, we can sometimes use this shorthand notation that means I goes from 1 to 3, alpha I, Vi. So sometimes we don't even write this I 1, 2, 3. It's understood that I goes from goes over all the index and it goes from 1 to the dimension of the vector space. And we write some alpha I Vi that any vector V can be written like this. Okay, good. So this is the definition for basis, and we know what the dimension is. Let's now discuss the next important concept. It's called the inner product. Some people also call it dot product, but we will exclusively be using this word inner product in this course. But if it helps you to remember, you can call it dot product if you like. So inner product is defined. You can define it actually in several ways depending on a vector space. The definition that I'm going to give is the one that is commonly used in this course, and that is that if you have, let's say, 2 vector V and W, so these are 2 vectors in the same basis in the same vector space, their inner product is defined like this. Let's say W, V, and we can define it like this. Now you can think of it like this: W into V. So this W is something that I have introduced now, and this V is already the cat V that we talked about earlier. This W is called a bra, and this has a relation with this cat W like this. And this dagger symbol means that I take conjugate and I take transpose. For example, if I have a vector W like 1 minus iota 2, then the bra W is, I also take its conjugate and transpose. So when I take transpose, the column vector becomes a row vector. So this 1, and then I need to take the conjugate. Conjugate means wherever iota comes, I change its sign. So minus iota becomes plus iota, and 2 remains 2. So this is my bra vector. So a cut vector is a column vector and a bra vector is the row vector. And if you have to construct a bra vector from the column vector, then you take its complex conjugate. And the inner product WV is now defined like this. So this W is W1 conjugate, W2 conjugate, W3 conjugate, and then the column vector is V1, V2, V3. And we use the rules of usual matrix multiplication. So W1 star into V1, W1 star into V1 plus so W2 star into V2, W3 star into V3. This is, so this inner product is a number. Okay, let me take an example. For example, if I have a vector V as minus iota 3 plus iota 0 and a vector W as 0, 2, 3, and we want to find out this time V inner product with W. So this is a column vector, this becomes a row vector iota 3 minus iota 0, 0, 2, 3. So iota into 0 is 0. 3 minus iota into 2 is 6 minus 2 iota. 0 into 3 is 0. So this becomes 6 minus 2 iota. And by the way, you can see that if we have evaluated W into V, this would have come out to be 6 plus 2 iota, which is just the complex conjugate of VW. So if you switch the positions, the answer is conjugated. Okay, let's now see what happens if we have a vector V and we find its inner product with itself. So it means that we have V1 star, V2 star, V3 star into V1, V2, V3, and this becomes V1 star V1, V2 star V2, V3 star V3, and this is V1 mod square, V2 mod square, V3 mod square. And you see this is a real number, okay, because these are the modulus square. And if it is a real number, this is always going to be greater than or equal to 0. As an example, let's say if we have a vector V like 2 iota, 3 minus iota, 1, then V is minus 2 iota, 3 plus iota, 1, 2 iota, 3 minus iota, 1. So this becomes minus 2 iota into 2 iota is minus 4 iota square. 3 plus iota into 3 minus iota is 9 minus iota square. 1 into 1 is 1. So this iota square is minus 1. So minus minus plus 4. And this iota square is minus 1, minus minus plus, and 9 plus 1, 10, plus 1. And this is 15. You see this is greater than 0. And by the way, if we want a situation that the magnitude of a vector becomes 1. So this inner product becomes 1. So what we can do is that I can define another vector V prime, which is 1 over V square root into V. So for example, in this case, this becomes 1 over 15 square root into 2 iota 3 minus iota 1. So now for this vector, if we compute this inner product with itself, this will come out to be 1. Such a vector is called normalized. And you will see that in quantum mechanics, we work with normalized vectors, and I'll explain the reason tomorrow. So these normalized vectors are very important for us. So that's why most of the time we are working with normalized vectors. So we work with a vector space in which each vector has been normalized. And it's very easy to normalize it. All we do is we divide if we have any vector, we simply divide it by the square root of its inner product with itself, which is called magnitude square sometime, and then we can get a normalized vector. Okay, so now let's define what we mean by orthogonal. So if we have a vector v and a vector w, and their inner product is 0, we say that v and w are orthogonal. And by the way, if they are individually normalized as well, then we say they are orthonormal. Orthonormal mean that vector v and vector w, they have a unit magnitude and they are orthogonal to each other. That's what we mean by orthogonal. And now if we get back to our basis again. So if we have orthonormal basis, and that's what we will mostly be working with. It means it's, let's say, it's a set of vector, let's say v1, v2, v3. If we talk about three-dimensional vector space, it has these properties. First of all, v1 is 1, v2 is 1, and v3 is 1. And v1 inner product with v2 is 0. v1 inner product with v3 is 0, and so on. It's just like you have I, j, k unit vectors in the real three-dimensional space, and all three vectors have a dot product with each other that is equal to 0, and all three has individually unit magnitude. So that's what we call an orthonormal basis. So we can symbolically write it like this, that vi dot product with vj is 0 when I is not equal to j, and it is 1 when I is equal to j. That when we have v1, then it is 1. When we have v1, v2, then it is 0, and so on. So this is an important orthonormality property that we will be using during the calculations when we analyze quantum algorithms. So any question regarding this orthonormal basis? So let me summarize. So we have a vector space that has a lot of elements in it, but there are few elements that can be used to construct all other elements by adding appropriately weighted superpositions of those vectors, and that small set is called a basis, which can be used to find all other elements. It's called, the technical word is spanning. It can be used to span the whole set. And now if the vectors in that basis, they are orthogonal to each other and they have unit magnitude, we call that certain set an orthonormal basis. And this is an important part of descriptions in quantum system that we will see tomorrow. Okay, so the next concept that we need is that of linear operators. Okay, by the way, let me just discuss one important thing, and that is, before I go, there is a special vector space which is used a lot in quantum mechanics, and it's called a Hilbert space. Hilbert space, and it also has another name. It's called inner product space. So it's essentially a vector space with an inner product defined on its element. and its vectors are all normalized. Okay, so this is just a vector space, but it also has an inner product associated with it that we have an inner product defined on these vectors. This is called a Hilbert space, and we will see that all quantum systems actually live in a Hilbert space, that they're defined by the vectors in a Hilbert space. Okay, so let's now go and see what are the linear operators. These linear operators we will see essentially will be helpful in defining quantum gates. But right now we are just talking in mathematical terms that they can be used at other places as well. So if we have a vector v, which is like this, v1 plus v2 plus v3 and so on, that I can write it like I1 to something and vi. A linear operator is an operator that if I apply it to v, it essentially can be written as an operator over all the components of this vector v, so that I can write it like I1 to whatever n a vi. So this is what we call a linear operator. That if we can write a vector as a sum of many other vectors, an operator on v, if it can be expressed as this new vector av, if I can write it as sum of the vectors by operating a on individual vectors that were making up this v, then this operator a is linear. And I'm not going to show it. You can check the proof in the book as if you like. But a linear operator can be shown to be represented by a matrix. So it means that if I have, let's say, a vector v, something like v1, v2, v3, then my operator a can be written as like a11, a12, a13, and so on, which means that I can work out this AV using the regular matrix rules, matrix multiplication rules. Okay, so let me give some examples, and since I will have to write a lot of numbers in this case, for example, I'm going to concentrate on this vector space of over complex vectors, and it's two-dimensional vector space, something like this, that has 0 0, I don't know, 0 1, 1 0, iota 1, and so on. So it's a vectors, it's a vector space of column vectors of 2 by 1 size. And first of all, you can quickly see that this element and this element is one basis. Let me represent it by, I don't know, something like v1 and this by v2, because I can write any other vector as a sum of these two vectors. By the way, a basis is not unique to a vector space. For example, this is an orthonormal basis. You can see that this has magnitude 1 because there's only 1 here, and this also has a magnitude 1, and they're both orthogonal because if I take the inner product of v1, v2, so this becomes 0 1, this is 1 0, so the inner product is 0 plus 0 because 0 into 1 is 0, 1 into 0 0. So they're orthogonal and they have magnitude 1. There are other possible bases as well. For example, I can define for this particular vector space a basis vectors like this. And you can see, first of all, they are orthogonal, because if I take W1, W2, I get 1 over under 2 into 1 over 2 as 1 over 2. So this 1, 1 becomes 1, 1. This 1 minus 1 becomes 1 minus 1. And 1 into 1 is 1. 1 into minus 1 is minus 1. So 1 minus 1 is 0. So they are both orthogonal. They are both orthogonal. And they both have magnitude 1. I have made sure by dividing it by square root 2 over here and here. So this is another orthonormal basis. So there are infinite number of orthonormal bases possible for any vector space. Okay, what you choose is depends, on your convenience or some other reasons of practicality. So there are always more than one basis vectors, more than one basis that are possible for any given vector space. All right, so let me give some examples of linear operators on this C2 vector space. So one example I can think of is the identity operator. Okay, if you apply this I to anyone, it will remain as it is. And this is, an operator. If you think about physically, it means that doing nothing to the vector. There can be, another vector. For example, I can have this. This operator x 0, 1, 1, 0, and let's see what it does to the basis vector. If I apply this x to v1 0, 1, 1, 0, v1 was defined as 0, 1. So this becomes 0 into 0, 0, 1 into 1, 1, 1 into 0, 0, 0 into 1, 0, and this is 1, 0. And this is the other basis vector, v2. And you can check that if you apply x to v2, you get v1. So this operator x changes basis 1 to 2 and changes basis vector v2 to v1. So this is sort of equivalent to NOT operation, because if you think of as in terms of a gate. So if there is v1 vector, this goes to v2, and if at the input you have v2 vector, it goes to v1. Similarly, there is you can think about another operator y 0 iota, and there are actually many more. And I'm listing these some special operators, because these x, y, and z, they are also Pauli matrices when we talk about a two-level physics of two-level quantum systems. They appear there, but for now they're just matrices. So this x, y, z, these are some operators right now, and we can actually show as well, if you want, that using I, x, y, and z, I can represent any other operator on this vector space only as a combination of I, x, y, and z. They're essentially the basis for any general operator on this on the vectors in this two-dimensional vector space. Okay, so any question on linear operators? So linear operators for us, they're essentially just they're like 2 by 2 matrices. So before I go on to the next topic, let me talk about just analogy with real space, a real vector, and a general vector space. A general vector space that we think about, is a collection of elements. And we have talked about that there are certain elements that are special. Sorry, my journal app has collapsed. Let me open it again. This unfortunately is The trouble with this thing that this sometimes collapses and some material that is not saved is lost. Okay, I think I'm fortunate that not much has been lost. Okay, so let me share screen again. All right, so let's talk about analogy with the real vector spaces. For example, if we have a three-dimensional vector space, three-dimensional real space. So there is this x-axis, y-axis, and z-axis. And I hope that you are already familiar with this thing that we can represent any vector using I, j, and k unit vector like this. For example, a vector A can be written as I hat, ai, j hat, aj, k hat, ak, where ai is x component, aj is y component, ak is z component. And in this form, I can write, as some index m hat, am, where m goes from I all the way to k. So we can represent this basis vector into the component along that basis vector. And if you have a given vector A and you want to find out what's its component, let's say along I unit vector. So what we do, we take the dot product of this I vector with A, and let's say you call it X component or I component, whatever. So we can find the component of the vector along a unit vector by taking its dot product with that unit vector. Similarly, we talk about a vector space that has, a lot of elements, and there are some certain special elements which form a basis, and that basis set is, let's say, v1, v2, and so on. And any general vector can be represented as some coefficient along these unit vectors, and where I goes from 1 to whatever is the dimension of this vector spaces. And these alpha i's, they are actually found by taking the dot product of this vector with the basis vector. So this inner product or dot product is essentially the projection of your vector onto the given basis vector. So if I substitute this alpha I back here, then I can write this v vector as I from 1 to n vi. So let me write this first, and then this alpha I, let me write it on the right side. So this is vi v. And since this sum is only on I can separate I1 to n vi over so v. So it means that this is essentially the identity, because this is v, this is v. So this is sum over I vi vi. This is the identity vector. Okay, so this is just an analogy between the real space and a general vector space. That just as in a real space we represent any vector as a superposition of unit vectors, and the component along a given direction can be found by projecting the vector along to that direction. So this is equivalent to writing a general vector in a vector space as a superposition of basis vector, and this component along a given basis vector can be found by projecting the vector onto that basis. Okay, so is there any question so far? Okay, if not, let me define another product that we will be using in this course, and it's called outer product. We defined an inner product, and we can also define an outer product. So an outer product is defined something like this. Let's say we have some vector v and some vector w. Now, instead of writing this w on the left side, I can write this ket vector on the left and the bra vector on the right side. So, and the way of evaluating this outer product is the same as before, that we can write this v vector like this: v1, v2, let's say v3, and then this is the row vector. Now this bra vector is on the right, but this is w1 star, w2 star, w3 star, and the matrix answer of this is, so in matrix notation, I hope you know that this, the first row multiplies with the first column. So this is, and that is our first element, v1 w1 star. Then this first row multiplies with second column, and we get the next element, v1 w2 star, v1 w3 star. Similarly, the second row, the first column, v2 w1 star, v2 w2 star, v2 w3 star, v3 w1 star, v3 w1 star, v3, sorry, w2 w3 star. So we now get a 3 by 3 matrix after the outer product of these two elements. This is the ket vector, and the second is the bra vector. So let me give a couple of examples. So let's say I have this v vector like 1, 0, 0. Let's work with two-dimensional vector space. I think that will reduce the amount of writing that I have to do. Let's say this is 1, 0 vector, and this w vector is also 1, 0. So what happens if I find out this v into w? So this v is 1, 0, and this w is 1, 0. So 1 into 1 is 1, then all three other are 0. And similarly, if I have, so this is essentially, if, so let's say we have v as 1, 1, w as 0, 1, then vw is 1, 1, 0, 1. So 1 into 0 is 0, 1, 0, 1, and so on. Now, let me introduce a notation that we are going to use anyway, that let's call this special column vector as 0, and this special column vector as 1. And we can see that this is a basis because both of these vectors are orthogonal. This is 1, this is 0. Let's now see what happens if I take an outer product of 0, 0. So this means this is 1, 0, 1, 0, 1, 0, 0, 0. 0 into 1, 1, 0, 0, 1. 1 into 0 is 0, 1, 0, 0. 1 into 0, 0, 1, 1, 0, 0, 0, 1, 0. Now 1, 1, 0, 1, 0, 1, 0, 0, 0, 1. Now we can use this notation actually to represent operators very conveniently. For example, let's talk about this vector x this operator x, which we wrote as 0, 1, 0, 0. So this is some operator x. Now I can write it like this: 0, 1, 0, 0 plus 0, 0, 1, 0, right? Because if I add these two matrices, so this is 1 plus 0 will be 1, this is 1 plus 0 will be 1. But this 0, 1, 0, 0 is this matrix 0, 1, 0, 0, which can be represented as 0 into 1. So it means that this I can write as 0, 1. Similarly, the 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, this one. So this is 1 into 0 plus 1 into 0. So it means this operator x can be written in terms of basis vector 0 and 1 using outer products like this. Similarly, if I have this identity operator 1, 0, 0, 1, I can write it as 1, 0, 0, 0 plus 0, 0, 0, 1. And you can see from above, this 1, 0, 0, 0 is 0 into 0. And the 0, 0, 1 is actually 1 into 1. And I can write it in shorthand notation like this: I goes from 0 to 1, I. This basically means that when the elements in this operator I are non-zero only when I and I are the same, and the coefficient is 1. So this is 0, 0 plus 1, 1. So that's why this identity matrix can be written like this, which I also, was talking about over here. Sorry, this is sometime erratic. So this thing that we were writing right here. Okay, any questions? Okay, let me, save this document because I'm beginning to feel like there is, some trouble with this document. Let me open a new one. That if it's going to be lost later on, not everything is lost.
So can you try saving as?
Okay, let me try that. That's a good suggestion. File save as. Let's say 1, 2. Still giving an error, so let's work with new node. Okay, any questions from you people? You seem to be, a lot quieter than I would have thought. Does it mean that most of you are familiar with this stuff? Okay, so not sure how to interpret this, but let's move on. Okay, so let me now introduce one other product. Okay, and this is called Tensor Product. And this is going to be helpful for us when we will be representing multiple qubit or multiple quantum systems. Suppose we have a ket W, a ket V, like V1, V2, and a ket W. Like this.
We can't see your screen. Like, just give up example.
Let me see. Let me stop sharing this and start sharing again. Now, is it okay?
Yes. Like.
This was not the one that I was working on. Okay. This was the one that I was working on. Let me save it. Okay, so suppose we have two cats, V and W. So far we have worked out the products like this, like bra V and cat W. So this is called a bracket, and this was called inner product. And then we worked out the product of cat and bra. This is called outer product. And this is helpful in representing operators. And now we are going to introduce the products of cats with cats. And similarly, we will be able to define product between bras and bras. So this product between V and W, it's written this cross in a circle. W is this V1, V2 tensor, and it's that tensor. So V1, V2 tensor, W1, W2, and it's operationally defined like this. You take the first element of this V1 and multiply with each of the element of the second entity. So V1 into W, V1 into W2, and then when you are done with everything, then you multiply V2 again with everything. So now this is a vector which is the tensor product of these two states. So conceptually, it's a little bit harder to picture it. So you imagine it like this: you have one vector space with let's say vectors V, and you have another vector space with vector W. And when we say the tensor product of these two vectors, we are essentially looking at another vector like this, which represents, if we talk about a quantum system, we can think about like this, that we have one quantum system in one vector space, and there's another quantum system in the second vector space. And if we want to talk about the joint state of these two quantum systems, then we use vectors like this that can help us write the joint state of quantum system in one and the second vector space. And operationally, these products can be defined like this. And not only that, we can define these tensor products of cats. We can also define vector products of these bra state. So then this W is, suppose, W1 star, W2 star, tensor V1 star, V2 star, and the rule is still the same. It's like this. So you pick one and multiply everything: W1 star, V1 star, W1 star, V2 star, then W2 star, V2 star, V1 star, W2 star, V2 star. So this is a row vector 1 by 4, row vector of size 1 by 4. And not only between bras, we can define vector product between operators. If we have, let's say, an operator for one operator and then the other operator, let's say this is some Y operator. So then X is 0, 1, 1, 0, and tensor Y operator 0, minus iota, iota 0. We work it out in exactly the same fashion. So 0 into 0, 0 into iota, 0 into iota, 0 into. So we take first element and multiply with each element of the next matrix. Then this 1 into 0 is 0, 1 into minus iota is minus iota, 1 into iota is iota, 1 into 0 is 0. So this is 1. So again, the whole matrix is repeated. This is 0, so we get 0, 0, 0, 0. So this is how we can construct the tensor products of these operators. And physically, we visualize it like this: that if we have, let's say, a quantum system Q1, and then there is a quantum system Q2, and this X tensor Y means that I'm going to apply X operator on quantum system in the first Hilbert space, and y operator on the quantum system in the second Hilbert space. And operationally, this works out like this. And when we want to apply this operator on this and this operator on this vector space on this quantum system, all we need to do first that their quantum states, this V and W, first we prepare their tensor product like this, then we prepare the tensor product of operators like this, and then you apply this matrix on this state, and the result will give you the result that would you get by applying x vector x operator here and y operator here, and the resultant quantum state will be given by this. Let me take a couple of examples here. Suppose I have a 0 state and a 1 state, and I want to write out their tensor product. First of all, by the way, there are several ways of representing it. Some people would just write it like 0, 1. So when you find it written two cats together without anything in between, it actually means tensor product. Some people are even lazier, and they would just write it like this, 0, 1. So this also means the tensor product of 0 state and 1 state. So this is the state of 1 qubit, and this is the state of the second qubit. And when I write 0, 1, this means that the qubit 1 is in 0 state, qubit 2 is in 1 state, and their tensor product is being meant by this 0, 1. Anyway, so this 0 state is, let's say, 1, 0, tensor 0, 1, and 1 into 0 is 0, 1 into 1 is 1, 0 into 0 is 0, 0. So it means if you have 2 qubits, so this vector then will give a state of the 2 qubit system that says that the first qubit is in 0 state and the second qubit is in 1 state. Similarly, 0 tensor 0 can be written as 1, 0, tensor 1, 0, and the result is 1, 0, 0, 0. So when you have this column vector 1, 0, 0, 0, and it represents a 2 qubit system, it means that both qubits are in 0 state, because there's a 1 here, and this vector is obtained by tensor multiplying 1, 0 and 1, 0. Similarly, this 1 tensor 1, this comes out to be 0, 0, 1, and 1 tensor 0 comes out to be 0, 0, 1, 0. So it means an arbitrary state A, B, C, D of 2 qubit system. Let's say you have qubit 1 here, qubit 2 here, and their arbitrary state A, B, C, D. It can be written as A times 0, 0, B times 0, 1, C times 1, 0 plus D times 0, 0. So these, tensor products of the basis states, they can be used to write any general joint state of this 2 qubit system.
आखिरी वाला 1, 1 नहीं होगा?
Sorry, 1, 1. Thank you. Thank you. So 1, 1. Okay. Let me stop here and pause for questions.